Now we'll see how integrals are used to quantify work. Before we get to that though, I need to talk about units. There are two systems of measurement that we're going to be working with, the US customary system and the metric system. And in the US customary system, distance is in feet, force is in pounds, and work is in foot-pounds. For the metric system, our distance unit is going to be meters. Force is in newtons, and we're often given things in kilograms, so we have to multiply by 9.8 meters per second squared, the acceleration due to gravity, in order to get kilograms into newtons. So keep that in mind. And then work is in joules. For each problem, we will be working either in pounds and feet or in newtons and meters. We won't be mixing the two systems. The reason we need to care about all this stuff is that work is equal to force times distance, or rather, the work done in moving an object is the product of the force required to move it times the distance that it's moved. For a lot of what we're going to do, the work, if you will, is to figure out what the force is that is being applied. We're going to start by looking at problems that involve springs. And so we need to consider Hooke's law, which says that the force required to maintain a spring stretched or compressed x units beyond its natural length is proportional to x. That is, f of x is equal to kx. Just let's quickly understand this here. I know it's a great drawing, right? Let's suppose we have a spring whose natural length is L. And what I'm about to describe is the same principle, whether we're in feet or meters. Let's say I stretch that spring a bit. The amount that I've stretched it is x. And what Hooke's law says is that the force required to keep this at a certain distance increases when the distance increases. That should make sense if you've ever stretched a spring. The same is true if we compress a spring, say x units shorter than its natural length. It becomes harder to compress the shorter it is, the more compressed it is. We aren't going to worry about whether x is a positive or a negative value. We're just going to know that stretching is longer than a natural length and compressing is shorter than a natural length. And that natural length does not show up in f of x equals kx. Notice that this is talking about the force required to maintain a spring stretched. This is just you're standing here holding on to the spring. But work was done in stretching the spring. That would be the distance in the distance portion of work equals force times distance. And then the force is kx. I feel like I'm already giving away all the secrets. I'll have to be okay with that. Hey, let's look at a problem. A spring has a natural length of 40 centimeters. A 60 Newton force is required to keep the spring compressed 10 centimeters. And the question is how much work is done during the compression. This one doesn't necessarily need a picture, but I'm going to draw one because I want to set this up for kind of a general process. So we have here a natural length of 40 centimeters, but we said the unit of distance in the metric system is meters. So I'm going to call that 4/10 of a meter. And we have to be really careful when we're reading these problems here. A 60 Newton force is required to keep the spring compressed 10 centimeters. Notice later in the problem we're asked how much work is required to compress the spring to a length of 25 centimeters. This 10 has a different meaning than this 25. This 10 says that I'm going to compress the spring 10 centimeters, which means that this distance here is 1/10 of a meter. It's not that I'm compressing it to a length of 10 centimeters, right? I'm only compressing it by 10 centimeters. Now let's apply this information that a 60 Newton force is required to keep the spring compressed 10 centimeters. We're using Hooke's law. F of x is equal to kx. The force is 60 newtons. So 60 is equal to kx. X is 10 centimeters or 1/10 of a meter. we end up with that K is equal to 600 if my math is correct. And since 60 is in newtons and I just divided by meters, this is going to be 600 newtons per meter. I'm not really so concerned that you're cool, that you have memorized the units there. But this K here is something called a spring constant. And it's not the same for every spring. It depends on the size of the spring, the size of the coils, what it's made of, all that stuff. So this is, let's call it unique to each spring. And what we've just done is we found that K is 600 for this particular spring. Now knowing the constant in proportionality, or the spring constant, 600, I can write down a general function for the force required to keep this particular spring stretched or compressed, and it's f of x is equal to 600x. Now let's talk about work done during the compression. So the idea is the spring started out this long, right? So from here to here. And then I'm going to change this arrow because I want you to think about the idea of compressing. Because of what Hooke's law says, it took less force to compress this spring at the very beginning of its journey than at the very end of its journey. The more I compress it, the harder it is to compress. We're going to think about a little portion in the middle. I don't mean the center, I just mean an interior subinterval. This is a subinterval, and guess what? Its width is going to be delta x. Now this is a tiny, tiny increment, right? Let's say that I'm moving this from x1 to x2. No, I don't like those subscripts. I'm going to say x sub I to x sub I plus 1. Because in my mind, this is getting bigger as we go to the left, because that's the distance that the spring is being compressed. Anyway, the incremental work done in moving the spring from that x sub I to x sub I plus 1, if delta x is small enough, is really f of x sub I times delta x, right? If this is a small enough interval, then we can think about the force being kind of constant over that interval. And if you have been paying attention to the last, 7 sets of videos, then you know that this I is going to be, we're going to have n of these iterations, and then n is going to go to infinity. And so this is really going to be an infinitesimally small width. Because of Hooke's law, we know that w sub I is k x sub I delta x. Now, in terms of work, of course, you can kind of see this. This is our force, and then that k times x sub I. And then delta x is our distance. So when we finally apply a limit and let n go to infinity for a sum of a bunch of these incremental widths, we get that the work is equal to an integral, in particular of f of x dx. And we have limits of integration, I'll call them a and b. So work is the sum of a bunch of force times distance. And in this case, the force is changing as the spring is compressed. Really important that I tell you that the force is changing. In this case, work is equal to an integral of 600x dx. The amount that the spring is stretched at the beginning is 0. It's at its natural length. And then at the end of its journey, it has moved an amount of 1/10 of a meter. So those become our limits of integration. The actual calculus is really straightforward. So 600x integrates to 300x squared. We're going to evaluate that from 0 to 1/10. 1/10 squared is 1/100th. And so this whole answer is 3. And the work done in the metric system is joules. So we'll say that's for the purple underlined bit. If we're now going to compress the spring to a length of 25 centimeters, and if it started out with a length of 40 centimeters, then we have a new integral. That work is going to be the integral from 0 to 0.15 of 600x dx. Right, because if I'm compressing it to a length of 25 centimeters, then I am compressing it by an amount of 15 centimeters. And again, the calculus is pretty straightforward here. 300x squared evaluated from 0 to 0.15. And that turns out to be 6.75 joules. Okay, but now let's think about this. This is kind of remarkable, so I'll remark on it. I know that was bad. Let me draw a different picture down here. We started out with a length of 40 centimeters, and the first problem said that to compress the spring an amount by an amount 10 centimeters, so 0.1 meters, that was 3 joules. That was for the purple one. We just found out that for the blue one, which compresses the spring 15 centimeters, let me make that a little bit longer there, it's 6.75 joules of work. So if it was 3 joules of work for the first 10 centimeters, then that means it was 3.75 joules of work for the next 5 centimeters. That's what's going on. As we compress the spring, it becomes harder to compress, and so more work is being done in moving it. Now, folks, the reason that we are using an integral is because the force is changing. Calculus is a study of changing scenarios. And so with a force that's changing, we need to use an integral.